Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to talk on module oil immersion objectives, quantitative metallography, image analyzer under vapor, characterization of materials 1. So students, let us see what we are going to learn in this module. In this module, the concept of oil immersion technique is described. Then, the various properties of immersion oil and the effects on the optical system are discussed in this module. The objectives, advantages, and disadvantages of oil immersion microscopy are discussed in this module. The quantitative metallography and its methods are studied here. Oil immersion is a method employed in optical microscopy to enhance the resolving power of a microscope. This can be achieved by submerging the objective lens as well as the sample in transparent oil having large refractive index, thereby increasing numerical aperture of the objective lens. Immersion oils are used in microscopy owing to their transparent nature, viscosity, and specific optical characteristics. Typically, oils having refractive index around 1.515 are preferred. The oil immersion objective is a specially designed objective lens which can be utilized in this way. After immersing in oil, many condensers give optimal resolution. All the diffraction orders need to be collected in order to successfully reconstruct image of the object. This ability depends on the refractive index and opening angle of the lens which is used. It can be defined as the smallest separation between two objects for the microscope to define them as separate objects. This minimum distance is denoted as delta. If two objects have a separation lower than delta, they will appear as a single object in the microscope. Resolving power of the lens can be measured from its numerical aperture Na as delta equals lambda divided by 2 times the numerical aperture. Here lambda represents the wavelength of the light which is used. Thus, good resolution, or I can say small delta, results from high numerical aperture which can be calculated as Na equals n times sine of alpha, where alpha naught represents half of the angle which is covered by the objective lens and n is the refractive index of the medium between the objective lens and the sample. Therefore, if the gap between lens and the sample is filled with oil, the numerical aperture can have values greater than unity, as oil has a refractive index greater than 1. Let us now study about the properties of immersion oil. Standardization of optical values of immersion oil has gained much interest in the past few years since it forms an integral part of the optical system of a microscope. Consistent values of immersion oil are essential to obtain good quality images from the microscope. One of the earliest attempts to standardize immersion oil was made by German DIN. Specifications 58884. These specifications are presently compiled by almost all European and American immersion oils, such as Cargill immersion oils. At present, United Nations International Organization for Standardization, that is ISO, is in the process of creating an international standard for immersion oils based on the DIN specifications. Specifications provide the value of refractive index of a specific immersion oil at one wavelength. The most often specified wavelength is mercury E line, that is 5461 angstroms. This wavelength is used since it lies near the middle of visible spectrum, where the human eye has maximum sensitivity. The mercury E line is indicated by DIN or ISO. Furthermore, various other immersion oils are also calibrated at sodium D line, that is 5893 angstroms, and helium D line, which is 5876 angstroms. An immersion oil at E line is specified to have a refractive index of 1.5180 plus minus 0.0004, that is GIN, or 1.5180 plus minus 0.0004 ISO at room temperature. Since the refractive index is similar to the glass used in the system, immersion oils contribute towards homogeneous optical path between the condenser and the objective. However, white light includes multiple wavelengths. Thus, for matching the refractive indices of all wavelengths in visible range with the glass optics, the dispersion value of the oil must match those of the optics. The dispersion is expressed as gamma of D is equal to Nd minus 1 divided by Nf minus Nc. As per DIN or ISO specifications, the room temperature value of dispersion of immersion oil should be 44 plus minus 5. An important concern for appropriate immersion oil is not of matching the refractive index for E line, as this can be achieved by designing several materials. Rather, materials having appropriate dispersion values are required so that dispersion can be closely matched in the visible spectrum. Among several materials that can be used to formulate the immersion oil, thickened cedar wood oil closely matches the glass optics and thus is the most commonly used immersion oil. However, cedar wood oil suffers from high absorbance of ultraviolet and blue wavelengths, yellowing with age owing to inconsistent volatility, as it tends to harden on lenses, acidity, and variations in viscosity. When diluted with solvent, it causes change in refractive index and dispersion values. For alleviating these disadvantages, synthetic immersion oils have been developed. Another factor which is impacting the performance of immersion oil is the temperature. The refractive index of most of the solids and liquids varies inversely with changes in temperature. Thus, the packaging indicates the temperature at which the oil has been adjusted. It has been recognized that a change in temperature by 1 degree from room temperature changes the refractive index of oil by approximately 0.0004. Thus, summers or heated ambient conditions have considerable impact on the refractive index of oil. The manufacturer data sheets usually mention the temperature coefficient for a particular oil. Majority of the manufacturers follow DIN or ISO specifications and use the oil which is standardized at room temperature, that is 23 degrees centigrade or 74 degrees Fahrenheit. However, oils have also been standardized for specific applications at 18 degrees Celsius, 20 degrees Celsius and 37 degrees Celsius. The calibration temperature is selected so as to simulate the temperature conditions of state encountered during working of the equipment. Most often used calibration temperature, that is 23 degrees centigrade, is slightly higher than the normal laboratory temperature, which is 22.2 degrees centigrade, thereby allowing for slight increase in temperature for radiated heat from the lamp of the microscope and other sources. The temperature can further be adjusted by slightly raising the room temperature. While using wavelengths other than D-line, such as green, which is 5461 angstroms, blue lines, which is 4358 angstrom, or near UV light, the refractive index can be matched to the glass optics by varying the temperature slightly in the area of slide, oil, and the objective. This required change in temperature can be determined from the temperature coefficient and dispersion value. Noticeably, with variations in temperature, the refractive indices of both glass and oil changes. Nonetheless, this change is negligible in solids and therefore can be neglected. Another important concern in formulation of immersion oils is the color, since its presence signifies the absorption of light and therefore leading to a loss of light. However, the exact influence of the color of oil remains to be studied. Whenever possible, it must be avoided, or else it must be offset by meeting other specifications. The presence of color leads to the formation of an absorption band at the wavelengths of monochromatic illumination. Specific oils have also been developed which can work at lower wavelengths, that is 3000 to 4000 angstroms as well. Immersion oil must have very low acidity. Synthetics generally possess lower acidities in comparison to the cedarwood oil. Higher acidity severely affects the metallic parts of the objective and thus can also deteriorate the lens cements. Lens cement is a seal which is used to prevent oil from penetrating to the back of the lens. However, the cracks or perforations that might be present in the lens cement draw oil by capillary action, leading to a thin film of oil sneaking to the back of objective. This gradually deteriorates the image quality, which might not be spotted immediately. This problem is very difficult to comprehend as it affects the microscope performance gradually. Most of the manufacturers immerse the objective in the oil while optimizing the particular oil to be used in microscopes. This test is conducted to verify various properties of the oil such as acidity, solvency, etc. In case of synthetic oil, proper care must be taken while selecting materials for oil formulation such that these materials must be immune towards oxidation, photodegradation, etc. In addition to this, the oil must be free from volatile compounds since they will gradually deteriorate the oil performance with time. Furthermore, any disparity in the temperature mentioned in specifications and that of stage leads to variations in optical properties. Deviations occurring from stage temperature are the most severe and must be considered carefully. Since the resolution of a light microscope inversely varies with the illumination wavelength, illuminations other than white mean, that is 5500 angstrom, such as green, which is 5461 angstrom, blue, which is 4358 angstrom, or near UV, which is 2750 angstrom, are often used. The resolution is expected to increase further in the UV region. However, special optics must be designed for the UV region. Quartz is often used to work in the UV region. Additionally, since near UV and UV regions belongs to fluorescent microscopy, the fluorescence of the immersion oil used in these regions must be either zero or very low. The fluorescence from the oil causes hazing effect in the field and blurs the images. For this purpose, oils of no or very little fluorescence have been formulated, such as sandalwood oil and other synthetic oils. A mixture of glycerin and water is often used in the quartz optics. Further, a mixture of sugar and glycerin can be used to minimize evaporation. In addition to this, for quartz optics, various stable non-hygroscopic immersion oils have been formulated. Oils having low viscosity are more likely to creep behind the objective when used in large quantity. However, these oils are used by some microscopists for small gaps between the cover glass and objective. In addition to this, low viscosity oils are often less suitable for retaining small bubbles. Due to the problems associated with the low viscosity oil, most manufacturers prefer high viscosity immersion oils. Highly viscous oils are suitable to fill larger gaps more effectively. Besides, higher viscosity oil can be reused so that second slide can be positioned and swung into place while retaining the contact with the oil drop which is left on the objective. Generally, oils with high viscosity are preferred because they offer more latitude with oil condensers because they fill larger gaps without any breaking and also avoiding re-oiling. Thus, viscous oils are advantageous for larger condenser gap, long focus, low power, oil immersion objective lenses, horizontal or sharply inclined instruments, and in microprojectors. The viscosity of the oil can be controlled by preparing blends of the different substances. Let us now study the oil immersion objectives. The oil between the sample and the lens enhances the resolving power by 1 by n. Cedar tree oil, where N is 1.516, was widely used prior to the development of synthetic oils in 1940s. The cedar wood oil objectives have the numerical aperture of approximately 1.3. The disadvantages of using cedar oil are that cedar oil takes up blue ultraviolet light, yellows with age, and is highly acidic and can damage objectives by repeated use. Also, diluting with solvent changes its viscosity. It must be taken off from the lens after use to avoid its hardening, as removal of the hardened oil damages the lens. New microscopy technique use synthetic immersion oils, thereby reducing the frequent problems. The numerical aperture values as large as 1.6 can be obtained with different oils. Synthetic oils do not solidify and therefore can be left on the lens without damaging it. Objectives that are specially intended for this purpose are called as oil immersion objectives. These objectives are generally employed at very high magnifications requiring large resolving power. In conventional microscopes, oil is applied to the microscope itself and stage is lifted, thereby plunging the objective in the coil, whereas the oil is indirectly applied to the objective in inverted microscopes. The refractive indices of oil and lens are similar. Thus, refraction of light on edging of lens would be small. For an objective lens, the correct immersion oil has to correctly match the refractive indices. Also, the spherical aberration occurs when inappropriate immersion oil or no oil is used with the immersion lens. Then the spherical aberration depends on the mismatch of the size of refractive index. Oil immersion is used upon rigidly applied samples, else the surface tension of oil can shift the sample by moving the cover slip. This can also occur in inverted microscopes as the cover slip is under the slide. We will now study the advantages of oil immersion microscopy. Majority of the manufacturers use oil immersion technique as it can be reused for second slide as well in specific conditions. Also, it can be used with wide condensers. Important advantage of immersion microscopy is that objective has long focus at low power. Also, this technique of microscopy can be used on inclined stages, example, horizontal and various slanted angles. Coming on to the disadvantages, the regular cleaning is required for appropriate functioning. Also, the chances of contamination by dust or other outside particles are high when the cements or adhesives employed for containing the oil under the slide are not properly placed. Then the cement may dry on the microscope, leading to degradation of lens or other parts of the microscope. We will now discuss the applications of oil immersion microscopy. Oil immersion microscopy relies on using one or more oils on an oil appropriate lens. These lenses can be used for studying inanimate or dead specimens. Most commonly studied samples are bacteria, muscle tissues with pronounced striations, as well as samples having small definable structures. Further, the samples to be investigated must not be sensitive to the oil because acidic oils may deform the specimen having metallic species. Let us next study the quantitative metallography. Quantitative metallography determines specific properties of microstructure via quantitative measurements, metallographic images. Quantities gauge comprise volumetric concentration of phases, grain size, particle size, and surface area to volume ratio of macro constituents. Now, the quantitative metallography methods. includes two ways. First one is the comparison method and second one is the measurement method. We will now discuss the comparison method, the quickest routine analysis method involving comparison of the microstructure images, that is micrographs, with a series of standard charts. Almost all modern microscopes include facilities to insert standard templates being reproduced simultaneously with the sample, thereby leading to rapid and easy comparisons. Various standard charts and templates issued by ASTM, ISO, and CIS correspond to the following measurements. First, measuring the grain size. Secondly, inclusion rating. Third, evaluating porosity of sintered carbides. And finally, classifying graphite structure in cast irons. The measurement approach includes the microscopic measurements are made on virtual image within the microscope, micrograph, and the ground glass screen. Modern microscopes are equipped with image analyzing facilities and other completely automatic quantitative measurements. Measurements are done by comparing with standard charts or templates. Secondly, it is calculated using square grid. Third is the measuring area of individual particles or grains can facilitate the measurement. The measured areas are divided by taking the square of linear modification, then straight lines are drawn on the image projected on the ground, glass screen or micrograph. Average grain size is given by total length of the lines divided by the number of grains intercepts linear magnification. So students, let us now summarize what we have learned in this module. In this module, the concept of oil immersion technique was described. The various properties of immersion oil and the effects on the optical system were discussed. The objective, advantages, and disadvantages of oil immersion microscopy were discussed in detail. Finally, quantitative metallography and its methods were studied. Thank you, students, for your attention.